Hi, this is Karen O'Brien, and we are going to continue this Tailings Dam study with video number 2. So in the first video, I talked about assembling the data and getting the data ready to build the model. And then in the second part of the video, we're going to go through and work through everything into the tutorial and then build the model in QGIS. And then the final video will be mapping and animating the mud flow, or the mud flow simulation back in QGIS. So I have used the two reports and I've opened them here and here. So we have access to that data, but we probably won't need it because everything is already built into the report. Again, remember, this link won't work unless you copy the whole thing, because for whatever reason, when I build the link, it always leaves off that final PDF. And so we start by loading the project into QGIS, and you know that this is the data that's available through Module 7. So again, if you don't have this, you have to send me an email. I will send you this data, but I don't have it posted anywhere for the time being. So you'll open this up. This is your QGZ. This is your model. This is your GPKG. QGZ sets up all your layers. This is the Tailing Dam Breach XML file. We'll take a bit of a look into that later. The Tailings Dam tool is here, or you can run it from QGIS. Either way, there's a little bit of extra data here. And resources for this project include this, which probably already seen most of these resources back in the previous model, or previous video, excuse me. And then we have the module export. Let's just take that and eliminate that. So we'll go ahead and run that here. And then let's see, module 7. And then this will be just a test folder for everything. Okay, so this is ready to go. So if I open QGIS, I've actually already loaded the model and I've loaded the aerial. So the aerial comes from here and the model comes from that QGIS file. And let's give this a quick look back at the tutorial, see what we do next. And the next thing to do is to locate that inflow node, which will be the location where we start our dam breach. So back in here in the model, if you go to the boundary condition editor and you just click on the inflow node, it will center your map right on the node so you can see where it is. Now this is the actual full model, but what you might see is probably just a placeholder hydrograph that'll just be like 100 CMS steady state flow hydrograph, and you won't see the actual dam hydrograph. So that's okay, because we'll be importing that later. Okay, we come back here and we run the Tailings Dam tool. Now, I will say that if you run the Tailings Dam tool from QGIS, that it's going to lock QGIS up. But I'm going to show you both ways to do that. Okay, so your Tailings Dam tool is here, and you need to point the location of the executable to this folder right here. So I'll just copy that. And I will paste that in here and just select the folder. And then this folder should be the place that, well, actually this one honestly doesn't matter. Just have it somewhere near this module 7. It really doesn't matter. And then this will be running your Tailings Dam tool. Now, if you load it up this way, I want to show you that you see it locks QGIS up. So instead of running it from here, it's just as easy until we fix that. It has some kind of execute wait statement in it right now, and it needs just an execute don't wait. So instead, you can just run it straight from the executable. And that way your map isn't locked up if you need something off your map. So now let's go back to I just want to follow along with the tutorial so I don't miss anything. Okay, so the next steps are to review the dam geometry, and then that will help us compile and enter the data into the Tailings Dam tool. Okay, so with the Tailings Dam tool, it's pretty important to set your units before you start the project. So it's going to default to English, but let's just set that to metric. And then we can, in this case, I'm just going to open the file because, so just click File and Open. And I will go to Module 7, and I want this guy right here. So I will open that file, and that will load the data that I've compiled already into this training. So that is right here, this XML file. And if you look at that in Notepad++, I'll make sure that nothing else opens here. Yeah, I've got a lot of stuff in here, so pardon me for that. I'll just get rid of some of this stuff. And there we go. Okay. Oh, sorry. Didn't need that either. So XML data is pretty easy and simple. It works with a lot of different kind of mapping programs. We'll see XML data or land XML data. But for the Tailings Dam tool, it's just basic line data that just fills out those tables and those variables for the Tailings Dam tool interface. So it's really super, super easy. You don't actually need to know how to review this or anything. Just recognize that that's what it is. And so there's a couple of things in here that you can grab from the dam geometry. So we'll start with the dam geometry. And we can get the height off of one of the plots from the report. This is from the periodical safety report, but you can also get this information from some of the data in the expert panel technical report. So again, the expert panel technical report is a post-failure report, and the periodical safety report is a pre-failure report that was updated in 2018. So from that, we get a dam height of 86 meters. I pull that straight off of the plot, and a freeboard of 5 meters. Again, that comes straight off of the plot. And a dam tailings volume. There's a table inside the report that has the volume of the solids, the volume of the whole volume of the dam up to the level of the tailings. And then this is the entire volume of the dam up to the crest of the dam. So this is too much volume. Okay, and then, so you can get this for your use this for your total volume estimates. And then we have some geotech data for the dam. Now this one is a little bit, I want to be careful right here because one of these is if you look at the report is in kilopascal, and the unit weight, cohesion kilopascal, the unit weight is kilonewton per meter cubed, and of course the angle of friction is just in degrees, so that's easy. These two are easy, but there's a little quirk right here where my cohesion of the dam material says it's in kilonewton per meter squared, but I kind of wonder about that. I kind of wonder if that's not supposed to be kilopascal. So let's be careful about that. And because if you look at kilogram per meter square, it's over 1,000. And if it's in kilopascal, it's 10. So I'm kind of thinking that this might be kilopascal, not kilonewton per meter square, but we need to check that with Noemi. So check that with Noemi before you put a variable in there. And of course, why did I choose this yellow, I guess, option right here? So this is not a single tailings dam. It is a series of tailings dams stacked on top of one another. And so maybe we have to use, and you can see here, these are the different water surfaces, in blue, for the different cross sections of the dam. And so you have to kind of maybe choose which one of these would be initiating the failure. And so you can try this simulation with any of these, but I just chose this mid-range value because it kind of represents this area down here. And again, it's a mid-range value. So it's a little bit easier because there's no zeros. That's kind of nice because there's no zeros in this cohesion column. I'm assuming we don't really want a ton of zeros for our dam material, even though, you know, this one right here doesn't have any cohesion. So you can try any of these. I don't know how sensitive these parameters are to the tailings dam failure. So I recommend just trying the range of them and seeing what you think. You also need the geotechnical data for the foundation of the dam system. It's not the foundation of the dam, it's the foundation of the entire area, which was from the report, silty clay between 5 and 11 strokes, or saprolite horizon between 15 and 40 strokes. There's two foundation materials down there that they measured. And so I chose, and then the unit weight is 20 kilonewton per cubic meter. So I chose cohesive soils and with a blow count of around 15. And I don't think this is a sensitive value. So you can start at 15 and you can try one at 40 and you can see if that's a sensitive parameter. I really don't think it is. And then the unit weight is your kilonewton per cubic meter here. You do not need the tailings material or the geotech data for the tailings because that goes into the mud flow model, not the tailings dam, but it is in here and grayed out because it's kind of more used as placeholder data. It's not actually used. And then let's see, does that take care of everything? Oh, the slope. Looks like the last thing I missed was the slope. So the dam height, the total impound volume, which actually I think the total impound volume, not impoundment volume, is not the tailings. So I'm going to go ahead and switch that to 80 or to 8 million cubic meters, not 8.6 million cubic meters. And then the impounded tailings volume is 7.5 million cubic meters straight from the report. This comes straight from the report. This I calculated off the graph out of the report. And this slope, if you look at this slope, what we have here is kind of like two slopes here. And both of them are fairly much 1.5 to 1. So you have a couple of options here, and the lowest option was in about the correct range. But what I didn't do is I didn't take like the slope from here down to here. I didn't take that as the slope of the dam. And I don't know how sensitive that parameter is. So you might, if you don't know what to use here, because your tailings dam is weird like this one, which I think a lot of these out there in Brazil are because they just are filling up a watershed, then you might see that you might try and test the sensitivity of this as well. Okay, then here are values in the tailings dam tool. And again, this one is probably just take that 6 out and turn it into a 0. Oh, and sorry, I missed a couple. The freeboard was 5 meters. The depth to bedrock was, I calculated off that, I estimated it to be about 2 meters. And the depth to the saturated tailings was a little also difficult because what I did is I took this cross section 3.3 off the dam, and I took the piezometer measurements from cross section 3.3, and I superimposed these piezometer measurements onto the plot of the dam profile by just like changing the white color to clear and then pasting this data and then trying to align it and scale it so that it basically matched up with the graph. And what you would see here is that like the maximum depth to saturated soils was 20 meters and the minimum was about 5 meters. And you can see we definitely have a problem with this dam, like right in here. You know, it's really not what you want to see. And then also down in here doing the same thing. It's just getting a little bit too close to the front edge of that tailings, and we don't want to see that. So in this case, I am going to use both of these and test it with one and test it with the other and see how sensitive that parameter is, okay? Because all this is all about sensitivity. Because as soon as the dam starts to liquefy and move through the system, all the geotech data is not as important anymore because the mud flow model takes over and it does its thing. So I started with a depth to saturated tailings at 5 and then went up from there. And Tailings Dam tool, this is your enter. And again, you saw that I just kind of backed that off a little bit because I thought I was maybe overestimating the total impoundment volume. And what else? Did I change anything else? I don't think I changed anything else. And I think originally in the report, I might have had that at 70 or something, but I don't know why I went with 86 instead. So probably not 70 and 86, probably not a huge change in tailings height from there. And then you just click the next button and that will take you to setting up the failure modes and finding your breach volume info. Okay, so let's try that. So we click next. And so our available storage changed a little because, oh wait, I'm sorry, wrong one. Sorry about that. Did anything change here? No, nothing changed here. So if the default for this is high, but if you set it to high, we get no breach. So the Tailings Dam tool estimates whether or not the breach will happen based on a statistical analysis of known tailings dam failures, and they kind of go into this interval of, oh shoot, what do you call that? This oh dang it, I'm sorry, my brain died. No problem. So bottom line is there are like as many historical tailings failures that we know of have taken the statistical analysis of those studies and put them in between two lines of approximate failure mode and based off of some of these conditions. So is it a hydrologic failure? Is there rainfall? And is it overtopping? Stuff like that. Is it a static failure? We have if so, is the reservoir level high? Is the pore pressure high? Or is it a seismic failure? And do you know any of the information about the seismic data? So we know it's a static failure because the report tells us that it was a sunny day failure, and that that there was no seismic activity except perhaps they were drilling a piezometer well around the time that the failure occurred, and that it was a wet season up to the season for that the wet season for that year was a little bit more precipitation than normal, and that's probably why the water levels in the piezometers were higher than anticipated. And that's why they were drilling a new piezometer well, because they were trying to measure whether or not the drainage and the pumping out of that tailings dam was effective. So this is a iron mine. So this is milled iron tailings. So it will be low, the particulate size will be low, but it doesn't necessarily have to have a lot of cohesive soil in it. It could be pretty sandy soil, I think is what they say in the report. And so the liquefaction of it is based off of kind of like finely milled sand particles. And so if you have a high reservoir level, it won't fail. I don't know why. You got to get with Noemi when you want to figure that out, to figure out why that won't fail. But if you set this to medium, it will fail. And it gives you a volume of the failure. So you can take the volume given to you that's calculated by, again, how much of a tailings dam typically fails in a given dam scenario. So that's still more of a statistical thing. So in addition to the volume of the dam, you know, how much of that tailing material is statistically left behind in a failure. And in this failure, not a lot of material is left behind. There's a bit of material left behind, but compared to other tailings dams, this one really fails like right to the bottom, and most of that material is failing out with the dam. So you can set this up. So it looks like we have 6.1, let's see, is that 6.1 million cubic meters, or we can put that up to like something a little bit higher. So you do have an opportunity to do user data, but I'm going to just stick with the Vmax. So I'll click the Create Inflow, and I can set this guy up here first to Vmax. Now the report states that the failure of the material happened really fast, and within the first 10 minutes of the failure, 75% of the tailings pond had failed and crossed the dam interface. So it's a super fast dam. So this variable is highly sensitive. So if you have, I'm going to try 0.5 to start with, and then this parameter, you're probably going to want to try entire event at 0.5 and then test it again at 1 hour and see if there's any parts of the model that get too much water and they go past the edge of the known failure, of the known kind of area of inundation of the failure, that you can easily discern from the red spaces on the map that happen right at, like within a month past the failure. The grid element is 7872, and we will take that straight from here. So this guy right here, if you click this tool and you click it, you'll see that that's 7872. That is our inflow node. And honestly, it doesn't really matter where you put it. You can just put it anywhere in here. I think I just chose this because that's where I got a coordinate off of Wikipedia from my previous video, and that was the location of that coordinate. And but you can honestly put that anywhere in this location and it'd be fine. That is not super sensitive. I just like to keep it up on the hillside so that the water is flowing away from it and not backing up and getting behind it, since our elevation data is already down to the bottom of that failure at this point. And let's get back here to this guy here, and I don't know about the porosity. I don't know what this variable should be. So if you have any questions about this, or you need to learn about this variable, you're going to have to get with Jim or Noemi, because I just don't know what to use. So I'm just going to leave it as default, and I don't know how sensitive it is. So you could leave it as default, or you could test the sensitivity of it. And this guy right here is the maximum sediment concentration. So Flow2D is a mud flow model, not a landslide model. So if you get anywhere above like 0.6, then you're getting up into more solid materials, and Flow2D does not model that really well. But I'm going to show you the video, and I'm going to show you why I'm going to start with a high sediment concentration, 0.05 or 0.5, 0.56. We can even try that. And then again, you can just do a handful of runs and quickly test the sensitivity of this. Testing the sensitivity of these parameters on this particular study takes all of about 3 hours to get in a handful of good runs. We are going to use the sediment concentration by volume, not the sediment volume, and I'll show you what that means in a second. And the failure pattern is just a front-loaded failure that happens very quickly, and again, that comes from the report. So let's go ahead and go to the next tab here, and I'm going to click on this, and then I'm going to take you to the video and show you why I chose this particular graph. So I'm assuming that our high concentrations were at the start of the simulation, and then as the breach formed fully and started moving through the system, the water became less concentrated and maybe less viscous and more fluid. And so I'm assuming high concentration at the start to low concentration toward the tail of the event. And let's go ahead and save the inflow.dat. And again, I want this to go to the inflow folder. So I'll click save right here. But then let's go take a quick look at that video, and we'll come back and review each of these parameters, and I'll show you why I chose those. So I am not, like I said before, I'm not a tailings dam expert, but there are some kind of obvious patterns in this failure that can help you address these variables. So let's start with the video. And if you see here, I'm just going to hit play, and we're just going to keep doing this a few times. So this thing just collapses all at once. And even look at this, just massive, like, I don't know if that's a tank of water or what, but just something is going on here. It's just bulging out, complete liquefaction in this lower part of the dam. And then the entire face of the dam is just pushed away from the dam as it collapses and just pushed downstream. Now we have a valley over here, and the milling stations over here, the processing and milling stations up here, and then the valley down here. And you can just see this material just pushing this huge lump of solids. It's not liquid at all. So this is not what Flow2D is designed to model. However, because this chunk of material gets, pretty much bypassed and maybe entrained into the sediment or pushed over to the side or maybe put up on a levee, that's okay to use Flow2D to model this because it gets really mud flow fluidy as the event progresses past this cross section right here. So it does become very much like a mud flow event once it kind of starts getting that material out of the way. And if you're down here on the, if you're down here in the valley, then that's going to be, even more so, because the valley is going to confine the flow, and that solid material is going to be pushed to the side up in the levees, and the frontal wave is going to push through, but it's going to become very much like a mud flow as soon as, it passes that certain time where that plug is pushed through. So that being said, we come back here, and that is why I chose this kind of front-loaded hydrograph, because from the report it said it was all occurring within the first 10 minutes, and 75% of the material had already breached and failed at 10 minutes in, and that lump of really high concentration material started at the beginning and then went down to something a bit more fluid as it went through. So we don't necessarily have to take this all the way down to 0.2% concentration. You can make adjustments to that and test that however you want once you get that inflow.dat file made. So we'll start out with our maximum concentration of 0.56, and the time of the event, again, you're going to try it at 0.5, maybe 1 hour, and see the differences in the model, because there is a difference. And the porosity is, again, I don't know what porosity means. And now let's go ahead and take a look at the inflow.dat file that we created. So this dude is right here. And what you get is the time in hours, and the in total event is 1.5 hour, because that's what we told it to be. And the start in the concentration, sediment concentration by volume, is going to start at 0.56, and then it's going to, just like the graph shows you, it's going to just kind of fall off. Looks like kind of a natural curve right here, kind of fall off to a lower concentration. And then you can make that adjustment on that final concentration. If you want that to be a little bit higher or whatever, you can do whatever you want to that concentration. And then this is the volume of the event. If you have the entire volume of the event goes, the volume of this is the water, and this is, the water with the sediment would be the percentage of the sediment that would be entrained into the water as the mud flow. Okay, and so this 0 means that it's an hourly simulation, not a daily simulation. This is the grid element that you see when you run this scenario in graphics mode. This will be the plot, the one that chooses to plot it. We only have one here, so you don't see anything else. F means floodplain, 0 means inflow, not diversion, and this is the cell we set it to. So now we can actually so we're actually done with this. So when you're done with it, you'll want to save it. I'm going to go ahead and save it back to that XML file right here. And then when you're finished saving it, you can exit out of here. And if you ran this from QGIS, then it's going to open QGIS back up to you so you can use QGIS again. And now that I built that inflow node outside of QGIS. So this is where it gets a little tricky. So you have to, if you want that to be part of your project, if you want to just use that inflow.dat file, you're fine. You can just use that inflow.dat file. But if you want it to be part of QGIS, you have to import it back into QGIS. So that method is, use this button right here to do that. And I'm going to just grab that inflow.dat file. Oh, sorry, actually, hang on a sec. Oh, maybe that's why I've been doing this wrong the whole time. Let's see. I need a cont.dat file. Okay, that's not going to work. That's funny. All right, so I need to export the project first. So let me export the project. Let's just call this the webinar test. And I'll go ahead and export that. Ignore this. It's just a weirdo issue I had. Okay, now I have that cont.dat. So let me grab that cont.dat and I don't know, let's see how this works. So module 7, webinar test. I'm just gonna see if this works or not. And I'm gonna put that in here. Now let's try this. Now if I import that, nope, I don't want to do it from there. I want to do it, I want that inflow node. That's the only thing I want. You can't do it that way. That's a bummer. Okay, so I'm gonna take this dumb inflow node and I'm going to put it into this webinar test folder. And then I will import it. So that was, remember when we set that up, originally it was just a dummy inflow node. Now I've done this several times, so this is actually the correct inflow node. But I want to show you, this is what you would do to get that information back in there. So webinar test, cont.dat, and then we just want the inflow node. I'm gonna click OK, and keep your eye down here because I'm wondering if at some point we kind of lose our boundary condition. I don't know why. So let's see. So when you bring that in there, you don't get it. You just have to convert it using this guy right here. And then this wipes out your outflow condition. So I don't even know if it's worth it. But whatever, we'll see what it does. Okay, and then, yeah, well, it seems like we're okay. We still have our downstream boundary condition. We're missing one. Let's see. And then we can name this Tailings Dam hydrograph. And then you can maybe name this something, like 50 or 30-minute failure, something like that. So the next one you could name like an hour or something like that. And then you hit that. Just to schematize it, I hit that. And let's see what happens. So, oh, you know what it says? That's funny. It said there were 76 of them, but I don't really think there's 76 of these guys. So that might actually be the problem. I might be duplicating some of those. Let's see what it does when you export it. Okay, now we're ready to export the whole thing because our data is reassembled. And so the model is kind of complete. And I click the export button here. Don't have any rainfall in this one. And we'll just take that here. And let's just see now. Yeah, just ignore this for now. We're just going to ignore that. Yeah, look, it's duplicated. That's odd. Now let's check that outflow file. Yeah, see, that's wrong. So the way that I fixed that was to take this dude here and delete it. And then we still do have quite a few points in there. So I'm gonna take this and I'm gonna edit this, and I'm going to just delete those. And then I will schematize it again. And now we should have wiped that data out. And now instead I will do this, and I will put, instead of using those points, I'm just gonna do it this way. So I built an outflow node using a polygon, using this tool right here, and then save, and then this guy here, and overwrite them. Oh, you know what? That's not helpful. I forgot to set this. Just give it a second. It takes a bit of time for this to work. Okay, let's do that again. I messed that up. Okay, and we're gonna have to wait for it again, I'm sure. Because it's trying to find, what it's doing is it's trying to find the edge of the map and find which of these is intersected to the edge of the map. That was a little bit faster. And then I'm gonna export that one more time. Whoops. And this time I will check to make sure our outflow nodes are in there. Yep, that's about right. And check, our inflow looks good. Yep, looks good. And then we need to set up the mud flow. So this is new. This guy right here is the mud flow and sediment transport editor. It's brand new, so the whole purpose of the webinar is to test this and get that video for that. Okay, so this is your tailings dam failure, or your tailings dam data. Okay, so you need the specific gravity of your tailings. You need a viscometer measurement of that tailings material and a yield stress measurement of the tailings material to get the data that you need for this. Now, if you need a little bit of resources on modeling mud flow, there are videos on my website. There's a whole series on mud flow modeling. There's a whole series on tailings dam failure that Noemi and Jim did to give you some more of the background on this. But there's also a couple of different resources. In the module 7, what I've done is I've collected the resources here. So you have the simulating mud flow guidelines. There is a table here that talks about the yield stress and viscosity as a function of sediment concentration, and it has a couple of test cases that you can use, and you can tweak some of these test cases. But remember, you have to know the material, what is the tailings, and when you are looking at the units on the shear stress and the viscosity of this, we're talking dynes per centimeter squared is the shear is the units of the shear stress, and poises is the units of the viscosity. So when you get the coefficients for that, those are kind of your final units for those two variables. Again, I'm not a mud flow person, so if you need more information on this, you go to Jim's documentation, or you ask Jim questions, or you watch his videos, and then all this will be just kind of like pointing you in the directions of other sources and giving you a bit of information about mud flow modeling. Now, you also have the data input manual that will give you a bit more information about these as well. So I'm not going to open it. You can open it yourself, but it has a mud flow page. And then once you set this up, these are just values that I took from another one of Jim's tailing dam studies. And I'm just going to export this. It's we only need the one switch. Don't need to check this. We don't have a basin to fill in this. And if you don't set a laminar flow resistance variable, then the model will calculate it from the end value. I'm gonna click OK, and that sets the variable. Then I want to just make sure that this switch is set to mud and debris, and then save that and export it again. And this time, well, I'm not going to export it again because I already did this, but I will open it back up to show you that sed.dat file because there is actually a problem with it. So you just want to make sure and delete that D line because you don't need it. You only need the M line. And that is a mistake. The QGIS isn't supposed to be writing that D line, but we already are fixing that. So by the time you get this, you won't have to worry about that. So I'm going to click save and close, and I will run this thing. Now, again, this is something that just started happening because JJ and Noemi were testing the model, and there is another wait command in the engine. So if you run your engine from here, it's going to lock your map up, which you may not want that to happen. So instead, for the time being, until we fix that, which it should be fixed also by the end of the week, I recommend that you just use the run for project folder, copy your engine straight out of there, and put it back into, so again, that was C drive program files x86 Flow2D Pro, run for project. Control A will select it, Control C will copy it, and then back to the project folder, Control V, and then you can run that from here, and that way you don't lock up your map. So okay. And again, if you're going to be running mud flow, tailings dam, sediment transport, or any kind of breach, you have to have build 21. Now I put this at a really fast output interval of 0.01 is my output interval so that you could see it. Otherwise, you see it here and then you see it here because it breaches so quickly. So my output interval is not 6 minutes. It's like a tenth of that. And I do have a bit of overflow right here, so I think I might be breaching this a little bit too heavily. So I might extend that out to, instead of running that out at a half hour, I might run that out to like 3/4 of an hour or test it at an hour and see if that kind of, because in the aerial, there's not really much accumulation of red earth right here, so I don't think it's getting up that high. But other than that, it seems to flow pretty close to the red mapping in the thing. And then I don't know, you know what? There might be like in the modern mapping, there's a dam down here, so you might be careful not to have that dam in here when you model this. Okay, so I will then stop the video here, and then the next video at the end of the tutorial will be the mapping of this, the animation mapping of this. So stay tuned for that video.